So we're looking at the least squares regression line here. And that's kind of our next part to scatter plots. Now, the least squares regression line is nothing more than the line of best fit. That's really all it is. It's the line of best fit. Its ultimate goal is to try to get as close to all the points as possible. Now, it can't please everybody, right? It's far from this point and maybe a little farther from that point. But ultimately what it tries to do is just fit all the points and get as close to them as possible. So in this example, I have GPA on the left, and I'll get rid of that last box there. GPA on the left and SAT score on the right. So I'm wondering if we can use GPA to predict a student's SAT score. So here's our GPA, here's their SAT score. You can see it's got a pretty strong correlation, and as you might expect, as GPA goes up, SAT score goes up as well. Now, we originally learned how to calculate the correlation. So if you remember that, we went over here, we hit the stat button right here, and then we went over to calc and did number 8, and I put this GPA in list 1, and I put SAT in list 2, and I did the regression and calculated. And then this is what popped out here, is on this screen. And there's our R value. You can see it's almost 0.95, which is a very strong correlation between GPA and SAT score for this example. So 0.95 is a pretty strong correlation. What we didn't look at was this A and the B. Alright, these A and B values are important, because if you look up here, it says, here's your equation. What this is going to do is it's going to spit out the equation for this line right here, the line of best fit. It's going to tell us what is its equation, so we can use it to make predictions. So it gives you the form y equals a plus bx. So it tells you that's what the form is, y equals a plus bx. But then it tells you what's the value of a, 43.13, we'll round, 43.13. So a, it tells us, is 43.13. I'm just going to put that in its place. B is 161.59. So it tells me that B is 161.59. See how I did that? I just took the y equals a plus bx, and I put the a in for a, and I put the b in for b. So this is my equation now. Now, you're probably used to seeing y equals mx plus b, right? Well, this is really the same equation, except we just put the b in front. So it's like b plus mx. See how that works? B plus mx. Still got a slope, still got a y-intercept. It's just written a little out of order. And then it says define any variables you use. So we know the a and the b here, we use those. What we need to define is what's y and what is x. What do those represent in our equation? And if you remember, our y list was list 2, or up here, our y values are SAT score, our x values is GPA. So I'm going to come down here and I'm going to say where y is the SAT score of a student, and I'll say predicted. Y is the predicted SAT score for a student, and x is their GPA. Just like that. Alright? Now we can use this equation to make predictions. So the first thing says, let's predict the SAT score for someone who has a GPA of 3.4. So here's our equation. GPA is 3.4. Is that going to go in for y or for x? Well, if you remember up here we said x is GPA. So in place of x, I'm going to put 3.4. And now if I want to predict what that student's SAT score is going to be, I just type into my calculator 43.13 plus 161.59 times 3.4. I get, so y, their SAT score equals about 592.5. Alright, so the predicted SAT score for a GPA of 3.4 is 592.5. We can do that again here as well. Alright, so about 2.9. I have a 2.9 GPA. What am I expected or predicted to get on the SAT? So I take out x because that represents GPA, and I took 2.9 in its place. And I just plug that into my calculator now. 43.13 plus 161.59 times 2.9. I get 511.7. So my predicted SAT score is about 511.7 for this model. We can also work backwards. All right, so here's my equation again. Notice I'm writing down my equation every single line. It says a student is predicted to have an SAT score of 600. What GPA would result in this prediction? So now I'm giving you the SAT. So I'm going to put that in for y. Remember, SAT means y. And now we're going to solve this equation for x to figure out what GPA should have been there. So the first thing I'm going to do is subtract 43.13 from both sides. When I do that, I get 556.87 equals, right? I subtracted it from this side and subtracted it from this side. And then I'm just left with 161.59x. And then at this point, since I want to get x by itself, I could divide both sides by 161.59. And I get x equals 3.446. So if you got an SAT score of 600, this line predicts that you would have a GPA of about 3.446. And we can double check that. Let's go up here. Check out a GPA of 3.446. It'd be about, maybe right here. Notice that takes us about over to almost 600 right there. So you can see that part of our line, the predicted part of our line, is at about 600 for that example. All right. Last thing I want to talk about is three more things. Extrapolation is trying to make predictions outside of our data's range. So what I mean by this is, let's say I say, I have a GPA of 1.0. What's my SAT score? Well, this is what we call extrapolation because 1.0 is very far outside of the GPAs we were talking about. Our data came from GPAs between 2.3 and 3.9. Right? Between 2.3 and 3.9. 1.0 is way back here. We don't know if our model is still good for those values. So we typically only want to make predictions inside of our data values. Interpret the slope of your regression equation. Well, here's our regression equation. Remember, the slope is always the one attached to x. So here, our slope is 161.59. Now remember, slope is rise over run, or it tells you if I go over 1 in the x direction, I'm going to go up 161.59. What this means is for every unit increase in GPA, we would expect the SAT score to increase by 161.59 points. What I'm saying is the slope is rise over run, so I go over 1, up 161.59. When I go over 1, I'm increasing the GPA by 1. So every unit increase in GPA, that means like from a 3.0 to a 4.0 or a 2.0 to a 3.0. Okay, every time I go up by a whole unit in GPA, the SAT score is expected to go up by this much as well. Okay, so in general, the template is this. For every unit increase in x variable, we would expect the y variable to increase by slope. All right, that's the general template for this. Okay, I want you to remember that. Almost memorize it. The slope says for every unit increase in x GPA, we would expect the y SAT to increase by this much. That's what the slope means. Last one, y-intercept. Remember that the y-intercept happens when x is 0. All right, so I go all the way back here when x is 0 on the graph. The y-intercept happens when x is 0. It also is this first value in our equation, 43.13. What this tells us is that a student with a GPA of 0, right? The y-intercept happens when x is 0. So a student with a GPA of 0.0 is expected to get an SAT score of 43.13. All right? I can't tell you enough. The y-intercept happens. This happens when x equals 0. When your x variable, in this case GPA, is 0, this is the value you would get. So a student with a GPA of 0 is expected to get a 43 on their SAT. Does this make sense? In this case, probably not. Not many students have a GPA of 0, and I don't even know if it's possible to get a 43 on the SAT. I think there's a minimum score. All right, and it would certainly not be possible, let's say, if our y-intercept was negative. You can't get a negative score. So most cases, the y-intercept may not make sense. In a lot of cases it does, but you have to think for yourself, does this practically make sense? Could a student really get a GPA of 0? Yeah, maybe. Could an SAT score of 43? Maybe, but it's probably not likely here.